So, welcome everyone to this new session. Hopefully, the last session in Javi's course on Marsden-Weinstein reduction. I think this is the last one, right, Javi?
Yeah, it will.
Okay, excellent. So, whenever you want, go ahead.
So welcome back, everyone. Those who were able to start the previous talks. Maybe you have to record it, or I will record it. Xavi, the talk. Hello.
Excuse me, did you say?
To
It's
record.
it's already been recorded.
It
It's
is
already
being recorded. I did it.
okay. So, welcome back. As I said, let us continue with the last part of my talk about the Marsden-Weinstein theorem. So let us recall a couple of things we were doing the last time. Okay, I already introduced what a symplectic manifold is. I introduced also Hamiltonian systems, and we were lately talking about the final results to start talking about the Marsden-Weinstein reduction. Okay, so in short, what it happens is that when you have a Hamiltonian system in a symplectic manifold, sometimes you have certain symmetries of the problem. I mean, the Hamiltonian can be invariant with translations or whatever, something of the sort. Yeah. So the funny thing is that sometimes if these symmetries are of a particular case, I mean, they are symplectomorphic, they maintain the symplectic structure invariant, it turns out that every symmetry of the Hamiltonian gives you for free another kind of symmetry, an invariance, rather, an invariance of motion. So it turns out that by means of a certain symmetry, which allows you somehow to simplify your problem, you get for free a constant of motion that allows you to simplify again the problem. So what it happens is that you can reduce the number of variables of your initial symplectic manifold in such a way that you will get a new symplectic manifold. Your Hamiltonian system, the Hamiltonian vector field, it will be able to be projected to a new manifold. It will be the projection, it will be again Hamiltonian with respect to this a new symplectic structure, and this is what is called reduction. Okay, so this is the main thing we are trying to do. Okay, so we start by a Hamiltonian system with respect to a symplectic manifold, and we have certain symmetries of the Hamiltonian function of the problem, and these symmetries leave invariant the symplectic form. Basically, they said that they give symplectomorphism. So it happens that by means of a certain symmetry in which direction the Hamiltonian is invariant, it turns out that we can simplify our problem assuming that this direction doesn't exist. Let us say this in this manner. And by means of these symmetries, we can obtain a constant of motion for each symmetry, a constant of motion that allows us to restrict the motion to a certain submanifold. So you see, for every symmetry, truly speaking, somehow you are reducing the dimension of the initial manifold by 2. Okay, so it turns out that if the initial manifold was even dimensional, by doing this reduction, the final will be even dimensional, and you will be able to, it can be proved that you can project your initial problem into a new problem in a manifold which is smaller, that is symplectic, and in such a way that the projection of the initial Hamiltonian vector field will be Hamiltonian, and you can again study a new problem. So this is the idea of the Marsden-Weinstein reduction theorem. Okay, is this process that it appears in physics in some, how to say it, in some manners without a clear meaning. Okay, but the mathematicians or mathematical physicists were able to put it in a that is in elegant form to explain what is going on in reality. So two things must be done in this seminar. The first thing is to describe Lie symmetries for Hamiltonian systems, and Lie symmetries of a Hamiltonian type. I will see what is it. And then I will use them to make a symplectic reduction. So, well, this has been, broadly speaking, what we are going to do. So let us start by doing this in a formal way, in a very exact way. So, okay, imagine that you have a certain Lie group action of a group Lie group G on N. Okay, let me recall that a Lie group is nothing but a group that it is also a manifold in such a manner that the multiplication and the mapping given for every point of the element, for every element of the group, its inverse, these two mappings are small. This is a Lie group. Okay, so we have a third Lie group acting on a manifold N. Okay, and when we have a certain Lie group action of this type, we will always denote by phi j, where G is an element of the group, a certain mapping from the manifold onto the manifold given in this way. It can be proved, okay, that this mapping is a diffeomorphism. Indeed, by the properties of the Lie group action, it can be proved that the phi of the inverse of G is the inverse. And you have these relations. Okay, so you have this. Please recall this thing and recall that every Lie group, for every fixed element of the group, gives rise to a diffeomorphism on the manifold. The second thing we have to think of is about the isotropic group of the Lie group action. And this isotropic group is fixed for every point X of the manifold. And what is the isotropic group? The isotropic group is the set of elements of the group, of the Lie group, that acting on X leave X invariant. Okay, so imagine, for example, that you have this sphere on R3, yeah, and you have the group of rotations. The group of rotations is SO3, and it is acting on R3 to R3. And imagine that you have a certain point in here in the axis Z. Okay, so you will see that all rotations along the axis, around the axis Z will leave this point invariant. So you can write that SO3 and the point Z, let us say that is 0, 0, 1, for example, this point here, okay, could be the set of rotations around the set, the axis Z. So normally this is written in this way. So too, indeed, you can see that all these rotations are indeed, they can be understood as rotations on the plane. So you see, this is the isotropic group, okay? And now we will denote by G and G star the Lie algebra and the dual Lie algebra of the Lie group G. Okay, so let me recall you that when you have a certain Lie group G, as it is given in here, you have a neutral element E, and you have the tangent space to the neutral element. This neutral space is called the Lie algebra of the Lie group. Okay, so it's denoted by G, and the G star is, yes, the dual. Okay, here also have the so-called exponential mapping. Okay, so let me recall you what is it, for those that don't know. The thing is, when you have a certain group, okay, it happens that you can define certain vector fields called the left invariant vector fields. Okay, why are they called left invariant vector fields? Because if you pick up a certain point of the Lie group, for example, E, and you pick up another point, for example, imagine that it will be G, okay, what it happens is that you have a mapping going from here to here. And this is the left action of the group. What does it mean? It means the left action of the group is a diffeomorphism of the group, mapping every element of the group with GH. Okay, so this thing is just the multiplication on the left by the element G. So this is a diffeomorphism on the Lie group. The inverse thing is this thing. Yeah, you can see it. And the funny thing is that when you have this morphism maps E into G. And so you have a tangent map to it. Okay, so if you have a certain vector, tangent vector at E, this mapping maps this vector into a new one in here. When the vector field is left invariant, it happens that the value of the vector field at G is nothing but the action of the vector field on E by the left action. So you see, for every point G, you can obtain the value of this vector field out of the value on E. So you can do this for every point G, the value at E determines the value of the vector field at every point. When you do so, you will be able to write, to define a certain vector field in the whole Lie group. Yeah, something of this sort. It happens that for every initial value at E, for every integral cube at E with a certain direction, you can write a certain integral cube with this vector field. Yeah, something of this thing. So you can write, you say that this is now T, this is an integral cube of the left variant vector phi with tangent vector at E equals to key. So if you have this curve, you can define the value of this curve at 1. And this is what is called the exponential of key, this thing. So the exponential of a certain Lie group is something that goes from the Lie algebra of the Lie group to G, and is such that we have a certain tangent vector of E, yeah? So we'll look for the left invariant vector field such that the value of E is equal to key. We obtain the integral curve of this left invariant vector field, okay? And we fix the value at 1. And this is the value of the exponential. So you can ask why this is called the exponential. Well, this is called exponential because when the Lie group is a matrix, this thing can be written to be the thing you already know from algebra, from analysis, for matrices. Okay, so that's why it's called exponential, but it's more general. It is something much more general than the thing you have. The exponential, you know, for matrices or for numbers can be understood as a particular case of this construction for certain matrix groups. Okay, but not every Lie group is a matrix Lie group. So the exponential is more general, that you know. Well, the second thing we have to know is what a fundamental vector field is. Basically, what happens is that when you have a certain Lie group action, a certain manifold, this Lie group action on the manifold allows you to determine a set of certain vector fields. And the way of doing this is by means of this definition. It's written in here. Okay, but let me just write an example of this definition, what is going on. So imagine something very easy. SO2, R2, R2. SO2 is the set of rotations on the plane. So you already know that they are just given by matrices of the form and they act on the plane. So you can define a Lie group action given by just multiplying by this. Okay. So once you have this action, okay, what you can do is just to think about this definition for this Lie group. In this case, when you have SO2, the set of matrices, the Lie algebra is called SO2, is the tangent vector to this, it can be proved that it's one-dimensional and is given by matrices of the form -1, 1, 0. This is also true. Where it comes this from? Pick up elements of SO2, things of this sort, with theta is a 13 element. Demand that this will be a curve passing by the neutral elements of SO2, that is identity. Make the differential of the cube at the 0 element, I mean the tangent vector to this cube at the element, and you will see that there will be things of this sort. Okay, this will show you that the tangent space this is included in this space, and if you pick up this and you make the exponential of this times a parameter, you will get a curve in SO2, and you will see that for every such a matrix there is a curve whose tangent vector at the identity is given by the element of this space, and the group and the curve belongs to the group. So it's a one-to-one relation, and you will obtain the Lie algebra things are things of this sort. So in this case, the thing is, this is a matrix Lie group because this is a Lie group. Okay, can be proved. And the exponential of matrices is just the typical, well, this matrix is just the typical exponential, So it's the sum is equal to infinite. Or if you multiply by 13 constant t will be t 0 minus 1 1 0 well, this. And if you make the calculations, you will say that it's nothing but this. This is the exponential, okay? 13. And this is a particular element of the Lie algebra. So what happens? It happens that when you have R2, this thing, okay, you can pick up every point of R2, and you can try to find out the way of the fundamental vector fields of the group action. So what do you have to do? Well, you pick up a 13x, and then you pick up a 13 element t key. Here we can suppose that this is this element of the Lie algebra. So when you pick up this, the exponential t key, this is nothing but this exponential, what you already know that you said it. Yes. And what you are going to see is that this is a curve in the Lie group, and this curve may act on this point, and by acting on this point, it will move it. You can see that this is nothing but a rotation with angle t. Yeah. So in which direction? In the minus direction downstairs. Yeah. Wait a second. 1 0. It was less. It was no. It was upstairs. Yeah, it's a rotation in this way. How to see it? Just imagine that you have this. The only thing I did to see the direction is to apply to 1 0 and obtain cosinus t sinus t. So an element that is in here, the image has the coordinates lower and the coordinates y is bigger than 0. So it goes this way. So when you have this x, these elements are going in this way, yeah? And the curve, the action of exponential tq acting on this point, well, let me write it instead of xy, okay, is moving in this way. So what you are doing next, okay, you have this thing, is to obtain the derivative of this in terms of time by t0. I mean, this is the velocity, the tangent vector to these q's at this point. So you see that this is the fundamental vector field related to this key, yeah? So you can repeat this on every point. Here it will be 0. It will be something of this, yeah? So the fundamental vector fields are those vector fields that are generated by the cubes of the type exponential t, yeah? So this is the thing you get, and these are called the fundamental vector fields, and somehow they describe how the action on the manifold looks, yeah? Okay, So in this work, in the Marsden-Weinstein reduction, we are very concerned with certain sorts of Lie group actions. And it turns out that every Lie group has different associated Lie group actions defined in a natural way. So if you have certain group Lie group G, you can define the right action. The right action is nothing that is an action of G on G. Okay, so this is the Lie group and this is the manifold which is acting. And for every element of G, you are multiplying on the right by the element G of the manifold, but by -1. Why by -1? Because to ensure that this will be an action, I mean that you have to ensure that this will be this, okay, to be an action. The only way of doing so is to multiply on the right by G-1. Indeed, you can see that this first thing, by doing as it's written, it will be R1, R2 will be this one. When you multiply by G1, the action of G1 will be -1. And you see, the fact that this is by -1 allows you to invert the order, to write this, and to see that this is the action acting on H. You see? So the -1 is a key to do so. When you do it on the left, you don't need anything. You just need to write the left action. You don't need any -1 or whatever. And then you have the action by inner automorphism. And this is why this is called E. And so the thing is that for every element of the group, you will act on the left by G and on the right by G-1. In many cases, this is written that this is the same as this. And this is sometimes useful, okay? That the action of an element of the group on H by inner automorphism is the same as multiply on the right by G-1 to H, and then on the left by G. So once you have these, you can define another very important actions on the Lie algebra of the Lie group and on the dual, okay? So this is called the adjoint action. It's very important in physics, and this is called the coadjoint action, okay? There are ways of modifying this action and obtaining different things, but these will be the main ones for us, yeah? So the adjoint action is such that you have G, given G, you have the inner automorphism, okay? But here you have an element of the Lie algebra. So which is the natural way of acting on an element of the Lie algebra, something that is in a tangent space to the neutral element of the Lie group by means of G? Well, you pick up the inner automorphism, you pick up, you notice that this on E lives invariant, so something from E to E, and then you pick up the tangent mapping to the inner automorphism G at E, so it will be something that it goes from the tangent space at E or to the Lie group to the tangent space at E of the Lie group. I mean, this thing. So this is a natural way. And if you want to do the dual, well, I'm very sorry, but here it must be -1, okay? The way of doing an action on the dual, once you have the action on G, is just to making the transpose and making the inverse, okay? The tangent space to the inverse. Again, the -1 is must be required in order to ensure that this is a Lie group action, okay? So it's a matter of calculation to show that everything goes well. The following thing is, this is an example, it's a very trivial example where the group is R3 and the multiplication of the Lie group is considered to be the natural addition. So this R3 with addition is a Lie group because the sum is indeed a smooth operation on R3. The mapping given for every element of R3, its opposites, I mean, minus the vector, is also smooth. So this is a Lie group, The Lie algebra of this Lie group, it can be proved to be just R3 again, the tangent space to R3, and the neutral element is R3, indeed. Okay, and now you have an action by automorphism on R3. It's a stupid action, but it's an action. And the thing is, for every element of R3, you have to act on the left by the element and on the right with the inverse of the element. But with respect to the addition, the inverse of the element is minus the element. And since the operation, the action on the R3 is abelian, this cancels with this. And it turns out that this action is array vector invariant. So as you see, the action by automorphism is indeed something that for every S gives you that every R leaves this point invariant. So the isotopic group of every element of R3 with respect to this action is the whole R3. It's everything. Every element of R3 acts on every element, leaving it invariant. So in here, by doing so, the action, okay, since this is the identity, the tangent space, the tangent mapping to the identity is the identity. So that joint action is the identity too. And the quadjoint action, since will be a minus, sorry, the tangent space to the inner action by means of minus R, this is the identity, the tangent to the identity is the identity, then transpose to the identity is the identity. So it gives that the quadjoint action is also the identity. So this is how this looks. And the following thing is to prove that every Lie group action in a manifold Q can be lifted to a new Lie group action on the cotangent manifold to Q. This construction is a little bit more tricky, okay, but it is not anyway difficult to prove, okay, because the thing is, you have phi and you have the Lie group, yeah, and you have the action in Q, and you go to Q. What you are going, imagine that you have this Q, okay? And you have a 13 point X, and you have that the action maps X onto Y, Y, as of an element J of the Lie group. Normally it is written in this way, okay? Instead of writing this thing, normally when we know which the action is, sort of notation is written this way. So you have this thing, and what you are going to do is just here you have the cotangent space to Q. So you can imagine that in this space you have a 13-4 covector, yeah? Let us say that's this thing. So you could like to map this thing onto something that is in here in the cotangent space, yeah? Because what you want is a 13 lift from T star to T star Q. And the manner of doing so is the following one, yeah? So you notice that the action phi j of X is Y, yeah? This thing. So that means that the tangent space, the tangent mapping to phi g at point X goes from the tangent space Q to the cotangent space at Y. So that means that if you put up, you work out the transpose, this goes from this to this. But you started here by something that belongs to the cotangent space to Q. And this gives you something that go the other way around from here. So to give this the other way, to turn these things, you can start by the -1 at Y. And this is something that goes from Y to X. You can transpose it. And this goes as you wished from this space to this space, to the cotangent. So the action of this mu X can be written to be the phi minus Y, Y transpose this thing, because indeed, by definition, the transposition, this will be this thing. Okay, so you will pick up something at y, this phi minus 1 tangent will pick up a certain vector, tangent vector in here, and then you will apply a new. So it works, it's what you wanted. So this action, okay, can be proved that it's an action, and indeed, if you pick up this thing and you pick up this, what you are doing is just t phi minus 1 gx, and then this thing, okay? And this will belong, as we want it, to this cotangent space, as we did here. So it turns out that this works. Indeed, this nice way of writing this, because you will notice it is written in this way, and given that something, it goes to some element gx given by the tangent phi minus 1 at gx tangent phi x, okay? And you can see that here you can project onto q and it gives you x, and here you can project onto pi and it gives you x, and it turns out that here this is the action. So you have a very nice commutative diagram for this action, okay? So the action, the initial action and the action extended, they are said to be equivariant, because when you act on the initial, by means of a group of the left action, and then you project, you obtain the same as projecting and acting by the same element by and the action down. So this is what is called equivariant. So once we have this, the following thing we have to think of is about momentum maps. Okay. So let me tell you where we stand. When we have these Lie group actions that they describe, normally in physical problems, they are used to describe symmetries of our problem. For example, transformations on the coordinates that leave the Hamiltonian invariant, things of the sort. So when we have many of these symmetries, and this is the way of describing these many symmetries by means of using a Lie group action, what we are going to construct is a certain mapping related to certain special symmetries that will allow us to find constant of motions of our problem. I mean, you have your Hamiltonian, as I told you, you have a certain group of symmetries of the Hamiltonian, and I will demand something on the Lie group action, and it will allow us to construct a certain new manifold, a certain new mapping, sorry, and it will turn out that this mapping will give us constant of motion for the Hamiltonian vector field associated with our Hamiltonian function. Okay, this will be called the momentum map, because it turns out that the coordinates of this momentum map will be indeed the momenta for the physical momenta for very important examples. Now, when the symmetries are translations, it will turn out on the cotangent bundle, it will turn out that the momentum map, the coordinate momentum map, will be the linear momenta. When we will have certain symmetries that are rotations, it will turn out that associated momentum map, the coordinates of the momentum map, will be the angular momenta. Okay, so, but there is a notion for this momentum map, whatever, and it turns out that for a certain Lie group action, that is the initial data we are dealing with, it is said that we have a momentum, a equivariant momentum map for this Lie group action when you have a 13 mapping that is from N to the manifold with the G star that is a dual to the Lie algebra Lie group, okay? And it works in the following way. If you pick up a certain point of the manifold X, X, and you act by the action as written in here, okay, and then you work out the value of the momentum map, this will be the same as acting by the momentum map on the point And then on this result, acting by means, again, this is a typo with the coadjoint action by J minus 1 on this. So it will turn out that this thing is of this way. This diagram is commutative. And when this diagram is commutative, we have a 13 action on N, we have 13 action on G star, and J is such that makes this diagram commutative. So it is said that J is equivariant with respect to these Lie group actions, the Lie group action on J and the coadjoint action on G star. So this thing means that the momentum map is equivariant. That's why this is called an equivariant momentum map. And the second property of the momentum map is the following one. It is that when you pick up the fundamental vector fields of the Lie group action, the contraction with the symplectic forms differential function. That means that this fundamental vector field is Hamiltonian. So the main thing about this is that when you have a Lie group action, you will say that you have an equivariant momentum map if all the fundamental vector fields of the action are Hamiltonian with 13 functions. These functions will give you just the contraction of G with the elements of the Lie algebra. In particular, if you pick up a certain basis of G, this will give you a composed with J, you will obtain the coordinates on J, and it will turn out that these coordinates are 13 Hamiltonian functions of these vector fields. Okay. So this momentum map is something whose coordinates, whose values are somehow Hamiltonian function fundamental vector fields of J. So let us put an example. I will recall the action. This would be a file, big, large file. And let us recall the action of R3 on R3. Recall that this is the action by translations. Okay, we already worked it out before. Yeah, you can leave this to the cotangent space. If you work out the things we did before, it will turn out that the lift of this action on R3 to the cotangent bundle, to the cotangent manifold of R3 will be such that the momentum is invariant, doesn't change. Yes, the phi, the action of the elements of R3, yes, move the R's, but they don't move the momentum. Okay, this is the way this extension that I recall you that this extension is something. This is the action of our group. In this case, is R3 on the cotangent manifold to the original manifold onto the cotangent manifold. So you will have this action, and you can recall that this action was defined in such a way that the projection onto the original manifold was equivariant. I mean, if you pick up the standard action by a 13 lambda, okay, and you project is the same as projecting and then doing the action by lambda, but the action by lambda is the plus. Yeah, it's just adding lambda to a certain vector. So this thing that goes here, okay, it must be some covector that projects to lambda plus the original vector, something like this. Now, if you work out the fundamental vector fields of the action offering on the cotangent by making the calculation, it turns out that these are just the partials with respect to the coordinates 1, 2, and 3. Omega in the cotangent, I recall you that it was defined to be something of this sort. Free. So when you contract with this, you will obtain the momentum. So now the momentum map is something that goes from the cotangent to R3. Okay. And it can be worked out that when you apply this thing, it turns out that the value of the momentum is just the momentum. So you see this J, okay, this momentum map is something that when you have the group of translation, The associated momentum map is just something that gives you the linear momentum. Okay, I can be proved that it's adjoint invariant, but this is quite trivial, so I will skip it because I want to focus on the things that are to come in the Marsden-Weinstein theorem. Let me explain you now what is the main object of all this stuff, and one of the most important objects appearing in symplectic geometry and physics. So let us define what is called a G-invariant Hamiltonian system. A G-invariant Hamiltonian system is a Hamiltonian system. I mean, manifold, symplectic on the manifold, a certain Hamiltonian function, which gives us a certain Hamiltonian vector field by means of the symplectic form. And then it turns out that we have a certain phi with a momentum map J. And we demand this Lie group action would be such that the Hamiltonian, the time-dependent Hamiltonian, will be invariant with respect to the action of phi. Okay, well, this maybe P is not the best variable. This is just one key on neither. I don't know how to call it. I don't know. X, no, it's not neither. X, Y, let's call it it's neither. I don't know, S, maybe, let's put this. Okay, a 13 point of the manifold P. Yeah, so it turns out that this Hamiltonian can be time dependent. Well, normally we assume that there's no difference on time, there's standard stuff. And the thing is that the action of the group on the point S leave H invariant for every value of T. Okay, and these are the conditions we are demanding. So you have a Hamiltonian system, you have a Lie group action that leaves H invariant, and it admits a momentum map. I mean, basically the fundamental vector field of the group action is Hamiltonian, basically. And there is a adjoint invariant condition. Well, I don't want to think about this adjoint invariant because it's not necessary, and also it's a little bit technical. So one of the most important things in here is that when you have a G-invariant Hamiltonian system, it turns out that the submanifold given by the inverse image of a certain value of G star, okay, here this value of the G star is said to be regular. This is just to ensure that this is a submanifold, okay. It turns out that this submanifold is invariant with respect to the evolution of XH. What does it mean? It means that this thing is tangent to thing. What does it mean? Integral Q's of here with a point in this manifold that remain in this manifold. So you can make a scheme of this and say that this is your manifold P. You have all the stuff, the P, omega H phi A, and the J goes to G star, the 30 manifold. Here you have a regular mu, and the anti-image of this thing is a 13 submanifold. You're here, and it turns out that when you have H, you have the Hamiltonian vector field. Well, it turns out that this is tangent to this submanifold. Okay, I mean that you start by a certain point in here, okay, the integral Q of XH passing here is always in this submanifold. So that means that your motion is restricted to this submanifold. So this is the important thing of this theorem, that when you have a G-invariant Hamiltonian system, the level sets like this of the momentum map, when there are so many folds, they're such that every initial point on this submanifold remains within the submanifold when the evolution of the Hamiltonian system acts. Okay, every particle belonging to one of these manifold evolving according to the XH to our dynamical Hamiltonian system will remain within this submanifold. And here you have an example of this. This is a very simple example. This is a free particle, yeah, on R free. So the Hamilton equations are these, okay, the standard ones, and it turns out the momenta are constants of the motion. Indeed, when you pick up the Lie group action and you send it to the cotangent manifold, it turns out that this action has a momentum map, and the momentum map is just for every point it gives you the momenta. So our stuff tells us that when you pick up a third time submanifold J minus 1p, okay, the evolution of our dynamical system fixes, allows you to tell that every point that belongs to this submanifold will remain in this submanifold. And it happens. You have a third time point in here, this point will have 30 momenta. And the evolution in the Hamiltonian system leaves the momenta fixed. So the evolution of this point with it here will remain in here because the evolution will fix the P, and these are the coordinates of the momenta. So you see that everything is fixed. So let us finish. This is the final point of all these talks. Let us talk about the Marsden-Weinstein theory. The Marsden-Weinstein theory, it has two parts, okay? Here you have the schemes of the things we have done so far. This is the level set of the momentum map. But please recall that when you have an initial point, you have still the action of the group leaving the Hamiltonian invariant, yeah? So the thing is that since the Hamiltonian is invariant with respect to the action G, somehow you can see that the elements that come from acting G on the initial point, they are somehow equivalent. You should think of it as being equivalent. That's the idea what you have. But on the other way, you know that the motion will be restricted to the submanifold given by the level sets of the momentum map associated to Lie group action. So on one way, you have to restrict to this submanifold. On the second way, within this submanifold, there are third time part which can be retrieved by means of the action of the group. Yeah. So the Marsden-Weinstein theorem tells us that you can consider on here the manifold coming from consider all the points that belong to this submanifold and can be connected by the Lie group action as a point. You consider a equivalent relation consistent on identifying all those points that belong to this level set and can be connected by the Lie group. When you do so, you obtain a new manifold that is symplectic. And it turns out that H, which was tangent to this, can be projected on the new manifold on this new manifold, which is given by making some kind of this here reduction. Okay, so the thing is that Marsden and Weinstein resume many results due to Lie, Cartan, Uriot, and all the researchers which studied this kind of reduction in particular cases. Okay, and they gave a nice geometric picture of this reduction. So the Marsden-Weinstein reduction theorem is exactly this. Okay, you start by means of a Hamiltonian system that is G invariant, and you will have a momentum map. The momentum map will allow you to restrict your motion to a certain submanifold, and the action of the group will allow you to skip third time submanifolds to identify third time points of this submanifold in such a way that you can construct a new manifold, project your initial problem into this new manifold, and on this new manifold, you will get a projection of the initial problem that will be Hamiltonian with respect to a new symplectic structure. So this theorem is based on a couple of results. Okay, an important lemma and the Marsden-Weinstein reduction theorem by itself. So the first thing is the first part of this important lemma going to the Marsden-Weinstein reduction theorem, the one that tells you that if you have the tangent to a certain point to the level set of the momentum map, this thing, okay, this thing here, and you have the action of the group that gives you an orbit, okay, this thing, the intersection of both is a tangent to a certain subgroup of the initial manifold. And the Marsden-Weinstein noticed that this subgroup of the group, which leaves this point within this manifold, is the isotropy group of the value of nu with respect to a coadjoint action. That's why I explain you why it is that joint action. They noticed that the subgroup acting on P and living within this level set was indeed the subgroup of G that leaves mu invariant, the isotropy group of mu with respect to the coadjoint action. So this was the first thing that Marsden-Weinstein noticed. The second thing is that the tangent space to this level set is the symplectic orthogonal to the tangent space to the orbit. The symplectic orthogonal means that if you look for all vector fields, tangent vectors, sorry, that contracting with every element of this tangent space with the symplectic form, it will be equal to 0. So there is a way of connecting the tangent space to the level set with the tangent space to the orbit of the group, and it's by obtaining the symplectic orthogonal. The symplectic orthogonal behaves much like the symplectic with respect to an inner product. So the symplectic orthogonal is the original space, okay? So using this, you can say also that the tangent, the symplectic tangent to the tangent space to the level set is the tangent to the orbit. So you see, there is a nice property linking both things, but notice something, and is that this relation is telling you that if you have the tangent space to the action of the isotropy group of P, this thing belongs to this space, to the tangent space to the group action, and belongs to the tangent. So all these elements belongs to this, and all these elements belong to this. So they are orthogonal to themselves with respect to the symplectic form. So you see, if they are orthogonal to themselves and to this space, it turns out that if you pick up the symplectic form on this space, it will be degenerated, because in these directions, and only in these directions, every vector here will be tangent to itself and to all the tangent space. So the symplectic, original symplectic form will be degenerated, and the kernel will be given by this space. So if you project onto a manifold, dropping this thing, the Marsden-Weinstein tells you that the symplectic form can be projected onto this manifold. And one of the reasons why this is possible is because its kernel, it will be indeed the kernel of this projection. And this is indeed the Marsden-Weinstein reduction theorem, that this thing can be projected, okay? And this projected manifold, that is the level set divided by the isotropic group with respect to the conjoint action of the value mu. This symplectic form here is one that is univocally defined, okay? And it is symplectic because it's like the original one reduced by the kernel. I mean, the only directions that make you to have problems to make this form here to be non-degenerate, they are dropped by this reduction. Since the omega in here is the pullback of the omega, the initial omega, it would be closed. So here omega is closed, but it's degenerated, and here it can be proved by the Marsden-Weinstein theorem that it's projectable. Since it's projectable, it can be proved that it's closed also, and it's non-degenerate because the direction of omega, where it comes from, that made this omega in here degenerate, the restriction omega to this tiny space degenerate, had disappeared. So let me just tell you to finish that this is just an example of a reduction theorem for a 30 particular symplectic form. There are lots and lots and lots and lots of Marsden-Weinstein theorems for all the structures. All the things in here, all the properties I recall you, they are keys to describe the reductions on all the sorts of geometric structure. They are for K-symplectic, they are structure, Poisson structures. In all these cases, the most modern cases, what it happens is that part of the ideas of this reduction work, parts of the ideas of this reduction do not work. Indeed, one of the most important problems, one of relevant problems, is the so-called multisymplectic reduction, Marsden-Weinstein reduction. In this multisymplectic reduction, the omega is closed, it's non-degenerate in a certain sense, but it's not a two form, it's a K form. The way of reducing this form, it's open so far. In short, the problem is that looking for invariance, looking for the way of restricting the omega photon as a manifold, and looking for the kernel of this form as a manifold, it is very, very difficult. And many of the things we did for symplectic manifolds, they work because we are working with a two-fold. If this is a free-fold for form, it does not work any longer. The fun thing is that symplectic manifolds are used to study mechanics. I mean, you know, Hamiltonian systems, they are just the integral cubes of a vector field, Hamiltonian vector field, and these are ordinary differential equations. When you have a symplectic, multisymplectic form, this allows you to describe field equations, and this can be used to describe field theories. Okay, so it's very interesting. There are particular cases, but there is no general solution for many structures or many cases of multisymplectics form. So this is all I wanted to tell you. It's 22 o'clock, it's 10 o'clock in the night. So thank you very much for listening to me for 3 weeks. I expect it was interesting, and any questions are welcome. Thank you very much.
Thank you, Javi. Thank you very much for your lectures, for your 3 lectures. Are there any questions or comments in the audience?
Someone is not sleeping? I hope no. I hope.
I think Jordi has a question, please.
Yeah.
Okay, I'm gonna do the thing. I don't have a question, I have a comment.
A remark.
A remark.
Remark. You have a remark. Okay.
First, thank you for the talk, because it's maybe the time that I understand better all the adjoining co-adjoint things. Because what I found is that there are books that explain all these silly things, but I always have it very hard to understand, because you are the first one that explained me why the definitions are how they are. And this helped me a lot, because they start defining things, and
yeah, indeed, I could tell you more how it's. Well, there are. I can recommend a work by. I think that it's Weinstein. I don't remember the old guy. I think that this was Marsden and Weinstein. And it's a recopilatory about introduction, it's a brief introduction to the symplectic reduction theorem. Okay. I have to recall it. Reduction is Weinstein. And the fun thing of this paper story. Let me just a while. Yeah, it's Marsden. It's comments on this, on the history, theory, and applications of symplectic reduction. So the nice thing of this work is that from the very beginning, it explains here the ideas by Lee, Basurio, Bad Meyer, and all, and how they started doing all these things by means, for example, the net field theorem, and for certain cases, and how step by step they were paving the way for the Marsden-Weinstein reduction theorem. Indeed, by means of this work, you can see why every structure works as it works, why it was defined when it was defined. So that's what I tried a little bit to describe. And also, I will tell you that some of the comments I told you, and things, for example, with this theorem, the fact that the symplectic or the symplectic the general one, okay, this word for symplectic and multisymplectic case does not work, and things of the sort, okay. So these are keys then to try to look for these generalizations. But about why everything is written, how it's written, and to understand fully why this construction is like it is, I recommend you this. It's very nice, it's very easy to follow, and it explains the Marsden-Weinstein theorem and also the Meyer one, because Meyer published a paper 1 year before, because the reduction by Marsden and Weinstein is 1974, but Meyer is 1973. But the problem with Meyer is that his results are a little bit less general. The stuff by Marsden and Weinstein is the important one. So if you want to know what to understand, or to listen again to everything I said, or even to listen to more things, this is the nice way to start with.
Thank you.
Thank you.
And there is a question then that what kind of Lie groups are really interesting? Because when I started to look at examples and applications, you have rotations, SUN, SON, SUN. Maybe if you are fancy, you put the Lorentz group. But usually in applications, you don't find anymore. And the question is, you have the same feeling that there is this limited set of groups that you have to know one the other year, whatever, or do you have find other groups that are interesting?
I mean, in my experience, but I used to deal with many kinds of examples. Normally, I used to find examples which are not typical, okay? I could say that you can find any Lie group, whatever you want, yeah? Anything you want, it is possible. I could say that the most important groups are, well, the ones you said, and it turns out that, as far as I remember, there are various groups, storic groups indeed, and they used to be related with integrable systems and things of the sort, and they used to be very important. There are a few ones, okay, that are very important. Some of them, they are important because it turns out that they have a simple structure. Some of them, they are important because physically rotations and translation and things of the sort, they used to be very important, yeah? So I could say that toric groups, I mean...
Well, the next step of Weinstein theorem is to say that every system can be, if it's compact, you can put it in torics in this kind of results.
I mean, there are many nice results about this, but I could tell the following thing. Mathematically, there are certain examples that appear with integrable systems and things of the sort, and it turned out that they are very interesting. They have nice mathematical properties, but they are pretty much studied. The problem, I mean, I can recommend you how he was called. Let me just, Alvaro Pelayo, I think. And if you want to see something about momentum maps and things, I recommend you, for example, is Alvaro Pelayo. If you write it on the Google, you will find his web page. and it's very interesting. And you will see that this guy maybe knew many people. Well, indeed, he worked in the Institute for Advanced Studies and things like that. And there are many relevant papers. Some of them, they are not new. They're just comments on symplectic techniques, momentum maps, and things of the sort. And in his website, you will find very nice papers. And one of them is about the momentum map. And it has very nice properties. And the important one, maybe it was this, Hamiltonian and symplectic symmetries.
Yes, an introduction. I see it.
Yeah, this bulletin of the American Mathematical Society. It's a wonderful paper. I mean, you can start by here, okay? This is something 53 pages long paper. And started by this, you will, it's an overview, okay? So there are lots of information. And if something is missing in there, you can take a look at the literature. Yeah, and they have a nice history about this topic. Some of the paper is nice because some of the topics he treated, they are basic, okay? But sometimes this guy is able to show you things that they are not used to be commented on papers. You know, something it's basic, but suddenly it has some comments like tells about something, and it turns out that this is not in the standard literature, and very interesting. And there you have momentum maps on toric actions and the Lie algebra of the toric action, and there are lots and lots of properties. You can read and you can find them whatever you want.
See, I'm looking at it right now. Yes.
Yeah. And I don't know, there are two symplectic toric many things. But just one comment, the last one. So far, for the last century, what it was important, it was the study of integrable system. Integral system and Hamiltonian system, for which if the manifold is 2n manifold, you will have n integrals of motions on involution. I mean, the Poisson bracket between the y plus 0. Now what is being studied is what happens when these integrals of motion, the coordinates of a certain momentum map, they are not in involution. They close a certain Lie algebra. And this is very modern, and they are important examples. So what probably, if everything goes as so far, you will start moving from this toric action that they were very cool so far, to things more complicated. Okay. So I could recommend these things because they're interesting. There are many properties, and I think that there are very good journals interested on this.
So you can find the strange Lie groups when you're trying to reduce a particular system, and you find that the group there is weird when you try to reduce it.
I could say that I am a little bit expert in finding weird examples that can be interesting. Okay. Another thing about the seminar. 1 second, because it's something interesting that people maybe don't know. Symplectic. Symplectic zoominar. It's very interesting. Symplectic zoominar. This is the symplectic geometry seminarium of the Institute for Advanced Studies in the United States. And as far as I know, it's open. Okay. So you can see what they are doing in that. Yeah, and you will see. Well, you can take a look at the web page, as always. And well, my boss in next year in Montreal is one of the guys who is administrating the seminar, and you will find that, for example, talk is for people you know. For example, Eva Miranda. Okay, people sometimes from the University of Barcelona. As far as I don't remember now the names, but I think that I saw a couple of guys. Whatever, the thing is that you will notice that symplectic geometry seems to be example, but it is far away from being that. I mean, there are lots and lots of things that are being doing about this thing. So, and well, I recommend the topic. Let us say this way. It's very interesting.
Thank you very much.
You're welcome.
Are there any more questions, remarks, counterexamples? Anything? No?
I have a question
Yeah.
Oh, please go ahead.
about the momentum map and
Yep.
like the naturality of it, because I found this definition with that co-adjoint action unintuitive. And could you explain more on that?
Yeah, let us say this way. First, this condition is not necessary. Okay, you don't need this for anything. The problem is that if you want to skip it, it would be problematic. You need more technical things, so that's why I put it. The second thing is that the reason of this thing, of this equivariant condition, is not really. It comes from another way. I mean, when the group G is connected, okay, really what this condition is telling you is that there is a Lie algebra morphism. You know, you can pick up the Lie algebra G, yeah, for every element. And as I told you, you will have the functions, the Hamiltonian functions of the fundamental vector field associated with this. So this equivariant action condition just tells you that if you map an element of the Lie algebra with its Hamiltonian function, this is a Lie algebra morphism. I mean that if you pick up the Lie algebra of the elements key, for example, 1 and key 2, okay, then the Hamiltonian of this, okay, it will be the Poisson bracket of the Hamiltonian of key 1 and the Hamiltonian of key 2. If you write this condition geometrically, yeah, it amounts to this, to the equivariance, but it is not necessary. Okay, you can skip it, but to skip it, you have to change this action. I mean, instead of doing the adjoint action in here, you can define something called the affine action, and it was the same. But the fundamental idea of this condition is that you need to ensure that the mapping going from the Lie algebra to the Hamiltonian functions will be a Lie algebra morphism. Means that it is not only linear, but also when you pick up the Lie bracket of two elements of the Lie algebra, the Hamiltonian function of this could be the Poisson bracket of the functions. And this is the only thing you need. And this is quite natural because it's telling you that basically the vector fields, the symmetries, these vector fields are somehow in relation with the relations between the Hamiltonian functions. Okay, so this is in reality, this is what you need, okay, in the theorems and what is used and why this condition is important. Yeah, but as I told you, this can be skipped even. Okay, the only thing you should do is just to change the coadjoint action by means of another one. This was, as far as I remember, it is written in the paper by Marsden and Weinstein. Okay, that there is written that you can modify the action G star to put another one, and then this one will allow you to repeat everything. But it's hard to find when someone uses this. Here's this. In most papers, what you will find is this or this. Many people don't know even about the fact that you can change these conditions, okay? Indeed, the conditions I'm putting here to make everything work, they are the standard conditions, but most of them, they are unnecessary. They are not really needed, okay? But this is, in many cases, much more complicated technically, is the first thing. Well, the reason why I skipped it was because it was difficult technically. The ideas, what we pretend to do, was already shown here. Okay, we could took 4 hours. There is another thing that, for example, here there are certain technical conditions. Mu is it's supposed to be a regular value of J. Well, it can be a so-called weak regular value. Okay. G mu is set to act freely and properly on this level set. This is to ensure that the quotient, this is a manifold. This is not necessary. Normally it is said that the action of G in this is quotientable. That means that this is a manifold, and this is more general. And you can skip certain technical conditions, okay? Even if this is not a manifold, there is now a so-called singular Marsden-Weinstein reduction. Related to orbifolds and things of the sort, are not new structures. And these are modern topics on symplectic geometry. So do you have any other question that this answers your question?
Yes, this answers.
Okay, thank you.
Are there any more questions or comments? I have a question, Javi. Now that you were talking about the necessity of this equivariant condition, where is the first place where someone found out that this was not needed?
Marsden.
It was Marsden himself
Yeah, Marsden and Weinstein noticed by themselves
in a later work.
Okay. Yeah, in his first seminar work. I'm not sure, but I think that Meyer didn't notice.
Okay.
This is one thing. I should check it out, but I think that was the point. Another thing I didn't say I want to get into is that I guess that I maybe remember that Marsden and Weinstein did this for infinite dimensional manifolds. So, but this is much harder than what I did. Indeed, in the infinite dimensional scheme, everything we did from the very beginning is not true. You have to put additional conditions. The problem is that in infinite dimensional things, you remember that at the very beginning we had a symplectic form, and I tell you that this mapping from the tangent cotangent is not degenerate. Yeah, that if this is equal to 0, that means that this is equal to 0. Yeah, and then I said that this means that there exists an inverse. In infinite dimensional, no. In infinite dimensions, you can have this is injective, but this doesn't mean that there is an inverse. So there are two kinds of symplectic manifolds: the weak, that are not degenerate, and the strong, where the inverse exists. The weak, there is no Darboux theorem. The strong, there is Darboux theorem. Okay, and the weak, many things are not known. For the strong, everything looks pretty much like in the standard case. Okay, this is works for quantum mechanics. Yeah, for infinite dimensional, but you need to deal normally with problems where the Hamiltonian and everything is smooth. There are no many, almost at all. I mean, infinite dimensional where the Hamiltonian is bounded is quite weird, very weird, extremely weird. So most of the things are not needed. I did with Julia Lang. I did this when we have a strong, but the Hamiltonian is not smooth. It can be done, yeah, but it's, if you allow me to say this way, it's crazy. Okay, it was her work, diploma work, bachelor's thesis, and it was very hard. I mean, it was crazy to do that. It works, yeah, it seems to, it works, but for very particular, well, not as particular, but the techniques are very, very involved. Okay, they deal with certain results about analytic vectors and manifold infinity dimensional functional analysis, non-trivial functional analysis, and well, it's heavy. It can be done. Okay, you can use it, but if you allow me to say that, you have to be a little bit crazy to deal with these problems, because it's the worst thing. Maybe it's one of the worst things I've ever done.
Well,
I've done
you are actually crazy.
So okay, I think that I hope this answers your question.
So no more questions or comments? Well, thank you again, Javi, for
You're
your
welcome.
lecture. Well, I have nothing more to say. Well, next week we will meet at the same place, same time. I will send you an email with the recording of this session and the title and abstract for the next one, which I can tell you it will be about Lagrangian mechanics and things of this sort. Probably a two sessions course.
Thank you, Xavi.
See you next week.
And see you next week then. Yeah. Thank you.
Yeah.